So first of all, let me thank the organizers for inviting me. And I was invited, so we had a discussion about the title, but then I read back to your original email and you explicitly invited me and said, I was hoping you could talk about higher representation theory. So I thought, okay, that has to be my title.
Tell us what it means.
Yeah, well, that's the thing. So I should preface this by saying I'm really, really far away from physics. I don't know, well, nearly no physics at all. I'm a very, very, very pure mathematician. And so my background is in sort of classical representation theory. And I think the idea of this talk is, so over the last 13 years or so with co-authors, we've been developing some higher representation theory, a representation theory of certain types of two categories, which are different from the types of tensor categories that are studied, say, by Ettinghoff, Ostrich, and people around that. So different from the EGNO book. And so I think the idea is to sort of throw at you what we've been doing to see whether any of that might be useful for you. I mean, in the end, I'll state some theorem, but I don't think any of you will be particularly interested in the theorem. It's more often more of a flavor of the kind of things that we do and what's on offer, so to speak. Okay, so and feel free to ask questions anytime, and I will probably not be able to answer, but I will try. So let's first start from very basic premise. Yeah, so representation theory, the motivation comes from physics. People were studying ages ago actions of symmetry groups on objects and so on. Yeah, so this goes back hundreds of years. I don't know quite how long. But then, so the first approach, the first very naive approach, is to just say, well, we have some sets, say the vertices of some polygon or something, and we have a symmetry group acting on that set. Yeah. And then, but then at some point, Frobenius came along and decided that it was far more useful to study linear representations. So instead of your set, you look at the vector space spanned by it. So you now have a linear structure. And instead of just looking at the group action, you linearize that as well, and you look at how the group algebra acts. So this is probably all really familiar to everyone here, or at least almost everyone. But then also geometrically, you get Lie algebras appearing as tangent spaces and Lie groups and so on and so forth. But they can be studied via their universal enveloping algebra. And then you can quantize that, you get quantized universal enveloping algebras. And I guess the upshot of this is that all of those group algebras, universal enveloping algebras, quantum groups are associative algebras. And so we can just study associative algebras in their own right. Yeah, and this is the kind of representation theory where I sort of grew up. Now, what do I mean by an algebra? And for the purpose of this talk, so I think everybody here knows what an algebra is, but what I mean by an algebra is it's a k-linear category which has only one object, or I could say finitely many objects. I don't really care. Yeah, that doesn't make a difference. Let's take one and call it bullet. And then what you probably think of as the algebra is really, sorry, I should have, what I wanted to say is what you really think of as the algebra normally is the endomorphisms of that bullet. Yeah, that's k-linear, so it's a vector space and it has a multiplication because I have composition. And so that's an algebra. And now, now a representation of A is just a k-linear functor from A to vector spaces. Yeah. So explicitly, it takes my bullet and sends it to the thing that I call a module. And it sends an algebra element, so something in my endomorphisms of that bullet, to what's, if you denote representations classically by rho, that's rho of A, which is now a linear transformation on your vector space. So that's my point of view. And so now that I've kind of said, okay, classical representation theory is k-linear functors from some nice k-linear categories to vector spaces. Now we categorify the whole thing and we look at k-linear two functors from certain two categories to something. Yeah, and the something will take a bit of care. Okay, so that's about, but that's my point of view of classical representation theory. So now categorification came along around the same time that I was a PhD student. So that is somehow how I got into it. Yeah, because it was very exciting. So categorification isn't really easy to define. What can be defined rigorously is decategorification. But again, just vaguely, this is just forgetting information. Yeah, so here's a table. If you have a set S, you could just remember the number of elements in the set and forget what the elements were. Or if you have a vector space, you could just remember the dimension, but forget whether it was column vectors or row vectors or polynomials up to that degree or whatever. Yeah. Then if you have a category, you can turn that into a set by just looking at the isomorphism classes of objects. Yeah? So you only look at, you consider objects the same if they're isomorphic, and then you just look at your set of objects. Now, if your category is additive, so you have some kind of direct sum construction, then you can define the split Grothendieck group.
You're not saying that's the unique decategorification of category, are you?
Well, I guess it depends on how you define decategorification. If you define decategorification, you can define decategorification in this way, that you take K0 and then that's that. But of course, you can also define decategorification very vaguely by just saying it's any forgetting of information. And then you could also just say, you just remember all objects. Yeah. So.
You did say decategorification was the easy one.
Well, yes, because it can be made rigorous, but you can also just have an intuitive idea of, and then it's less precise. So if I make it completely rigorous, then yes, that is the decategorification. So now if I have an additive structure, on my isomorphism class of objects, I can define an addition by just saying that I artificially make the isomorphism class of a direct sum equal to the sum of the isomorphism classes. Yeah. So in other words, I take the free abelian group on all isomorphism classes and I quotient out by this minus this minus this. Yeah. Oh. Okay. So now if I have a monoidal category or a two category, then additionally I have some kind of tensor product, or horizontal composition is what it's called in a two category. And then of course, in addition to, so that's usually an additive category, then I have this kind of thing. But now I can also define a multiplication by doing the same thing with tensor products. Yeah. And then I get an algebra. So somehow a two category or a monoidal category, which is a two category with just one object, decategorifies to an algebra. And so of course, if we want to categorify classical representation theory, we need to go the other way.
So here you mean by monoidal category, you're assuming it's also additive.
Yeah.
So it's like isomorphism goes to equality in some way.
Yeah, exactly. And then more generally, if you take an n category, you can take the n-1 skeleton and that's, but I don't go higher than 2 because I find 3 quite scary, because then you have to be super careful about which bits you keep strict and which bits you do weakly, and I don't know what a good choice is, and so I've never gone there.
Is the skeleton? Skeleton?
Skeleton.
Skeleton of the n category get the n-1.
Yeah. So it's, I mean, it's essentially you forget all the n morphisms. So an n category has objects, one morphisms, blah, 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 up to n morphisms. You forget all the n morphisms apart from the isomorphisms, and you consider the isomorphisms as equalities. That's this thing. Yeah. Okay. So categorification is going in the opposite direction, but it's very obviously non-constructive. Yeah, because even in the baby case, if I tell you the number 3, you can't possibly guess what 3 elements I have in my mind. Yeah. So it's not constructive, but you might hope that sometimes you might stumble across things that are categorifications of other things. And this is precisely what happened in representation theory. So people just observed that, so there's category O for a Lie algebra. So I think most people have heard of Lie algebras. Category O might be less familiar. It's somehow, so if you have a finite dimensional complex semi-simple Lie algebra, then you can relatively easily classify finite dimensional modules. That's a semi-simple category, and it's very pretty, but most modules aren't finite dimensional. And so that's sort of the next level of complexity where you allow some infinite dimensional modules, but it's still somehow controllable. Yeah. And on those you have certain functors which come with translation functors are precisely functors where you tensor with finite dimensional modules. That's the definition of translation functor. And then people observe that these satisfy relations. If I just compute, well, if I do the functor twice or something, they satisfy the relations of a Hecke algebra. Yeah, so this was kind of intriguing. And again, people might have heard of Hecke algebras because they somehow have some physicsy origins. But yeah. Then on the other hand, you have some affine Hecke algebras, which come, I mean, yeah, it depends. So they show up in lots of different contexts. One way of saying this is this shows up for finite groups of Lie types, and this shows up for p-adic groups in the same way. But now you have they embed into each other, so you can embed somehow Hn-1 in a fairly canonical way into Hn, or technically you have to take some parabolic to embed, but that all works fine. And if you look at certain direct summands of induction and restriction between them, then they satisfy the relations of a Lie algebra. Yeah, so those are just sort of observations that people came across, and that were very
Unwrap affine Hecke.
yeah. So yeah, sure. And I mean, this is sort of yeah. So on the it depends on how you want to phrase it, but usually you would say on finite dimensional representations of affine Hecke algebras. And I'm being very, very vague here. Yeah, because to make this precise, you have to so I said so you really embed a parabolic, and then you have a parabolic n-1 inside n, and then you have to specify what you want to do on the 1 bit, and then yeah. But anyway, so there are affine Hecke algebras. There are some Lie algebra actions, functorial Lie algebra actions showing up on affine Hecke algebra modules, and there are some functorial Hecke algebra actions showing up on category O for a Lie algebra. Yeah.
For the first bullet point, you said translation functors are tensoring with finite dimensional. So wouldn't those satisfy the relations like the fusion ring or the representation ring relations? Is it like a
well, yes, but that turns out to be
I see.
more or less the Hecke algebra. Yeah. So it's complicated because there are lots of different blocks. So and if I just pick an arbitrary finite dimensional simple module, that will split into a direct sum of lots of different functors, and then you have to look at the indecomposable components, and then you have to
But it's usually a quotient of the Hecke algebra.
What do you mean?
Well, so if in particular you're looking at SL2, it'll be the Templey-Lieb quotient.
I don't know.
So this is true,
Yeah.
but they satisfy more relations.
Yeah, I mean, it depends on what you're looking at. Yeah. Anyway, so this, yeah.
You're saying that the translation functors is some sort of categorification of the Hecke algebra, and
Yes.
and then the other way around. I mean, not the other way. You know.
And the Lie algebra, the enveloping algebra of the Lie algebra is somehow categorified by this.
Mhm.
So this is then what led to the whole concept of categorification in representation theory, these instances that people just observed. So why would one want to do this? Well, the higher structure has more informations because suddenly we can look at natural transformations between these functors. Yeah, if you just have two endomorphisms of a vector space, how would you I mean, that's just two functions, but suddenly we have new information coming from natural transformations. And so this can now give us new information about the decategorified object. Yeah, so one example is that we'll see that later. So there's a specific basis of Hecke algebras, which is called the Castellan-Lustig basis, and there were conjectures on the structure constants when you multiply things in that basis. And so they're polynomials and some variable, some parameter q. And the conjecture was that these have positive integer coefficients, for example. And so in principle, if you just know it's a number, how on earth would you show that it's a positive integer? But if you know it counts multiplicities of some indecomposables in some decomposition, well, these are positive integers by construction. Yeah, it's this sort of thing that makes categorification really useful. Okay.
Similar phenomena to say, like, if you have combinatorics and you use representational theory or something to study combinatorics.
Yes. It's the same kind of idea. Okay. So examples of categorification and representation theory is, so lots of Lie algebraic objects have been categorified. Kac-Moody algebras independently by Jovanov Lauda and Raphael Rouquier. And the idea behind that is the hope to construct 4-dimensional TQFTs, because from Kac-Moody algebras or quantum groups in general, you get 3-dimensional ones. And so the hope is that if you can go up. The problem is that in order to do that, you would need to, so there's always this parameter Q floating around, right? The quantum parameter. And what's been categorified as generic Q. And in order to get meaningful 4-dimensional TQFTs, you would need to do this at roots of unity. And that's only been done for Pth roots of unity, where P is a prime, and only really for SL2. And so this is a whole big other problem. But generically, these have been categorified. Heisenberg algebras, Lie superalgebras. Then there's something that people here are probably less familiar with, Hall algebras for quivers, but they're very closely related to quantum groups. Say that. And also the thing that is most important for this talk, because I want to say something about it, is the categorification of Hecke algebras via Zergel bimodules, which somehow are very closely related to these translation functors on category O. And so with those categorifications, so they were intrinsically motivated by representation theory, because lots of progress in representation theory has been made using those categorifications. So for example, Zhuang and Rouquier Ruiz abelian defect group conjecture for symmetric groups, whatever that may be. Yeah, it's just a big conjecture that was open for a long time. They did that using SL2 categorification. Then Ben Elias and Jordi Williams improved the Castellan-Lustig conjectures for all Coxeter systems algebraically using Zergel bimodules. Jordi then exploited that to give counterexamples to big conjectures. So the most important is Lustig's conjecture, which I think people really believe to be true. And so this is sort of a conjecture on algebraic groups, character formulas for algebraic groups. And Jordi Williamson found counterexamples to that by digging into Zergel bimodules. And that has since led to refinements of these conjectures, things that might still be true. So there's been a lot of progress inside representation theory coming from those examples. And so this, I guess, so when all of that was happening, Walter Mazurczuk and I at some point decided, okay, people are doing things in each example. So we want to have some kind of theory that covers all of these examples. And then we try to axiomatize what sort of properties they have in common, and so on and so forth. And that led to the theory that I'm now talking about. But you might ask how one would categorify something, because I said it's non-constructive in principle. But often algebras which show up in this context somehow appear as convolution algebras of functions on certain spaces. Yeah, so for example, one definition of the Hecke algebra is B cross B invariant functions on G. A group, so a connected reductive algebraic group. So if you take GLN, just invertible n by n matrices, then B is the Borel. You can take the upper triangular matrices, and now you look at functions from all invertible matrices to C, which are invariant if you multiply on the left and the right by elements in B. Yeah, and that's one definition of the Hecke algebra. And now you can say, well, okay, if I have functions on something GLN, if I look at GLN over C, that has some kind of manifold structure or algebraic variety structure and so on. So instead of just looking at functions, I can look at sheaves. And suddenly I have morphisms between sheaves. Yeah, so I get an extra layer. And so, I mean, this is again sort of just a vague intuitive idea. You can't just take all sheaves. You have to look at perverse sheaves, which are certain complexes of constructible sheaves with certain homology properties, but whatever. Yeah, so this is sometimes possible, but then the problem is that doing computations with sheaves is ridiculously hard. Yeah, so then people try to find more algebraic descriptions, and in the case of Zergel bimodules, this is due to Zergel in the original case, because he managed to get this down to just bimodules over algebras. Okay, so let's first, before we talk about Zergel bimodules and two representation theory, say, okay, let's agree what a two category is. So just to get everybody on the same page. Okay. So it's a category enriched over the monoidal category of small categories. In particular, when I talk about categories, I will always mean small category. Yeah, I don't want to get into any set theoretic issues. So what that means explicitly is that I have some objects. And from one object to another in a category, I need some kind of Hom set. And in this case, my Hom set is again a small category. So this will be the morphisms, and of course my category Cij of morphisms will have objects which I call one morphisms and morphisms which I call two morphisms. So very often these are also called one cells or two cells. So I think this is the more classical thing, and I'm getting old, whereas younger people usually talk about one cell or two cells. Okay, so then in a category I need to be able to compose things meaningfully. And this composition, if this is a category and this is a category and this is a category, I better ask the composition to be a functor. Yeah. So that's that. And then the other thing that other piece of data I need for a category is identities on every object. And so I just need some identity one morphisms. And then I have some natural axioms, which for a two category, I want to be strict. So strict associativity, strict unitality, and so on and so forth. So I am going to talk about two categories mostly, but for none of what I'm going to say is this going to matter at all. So it'll all work for bicategories. If you prefer those, it just very often is easier to do things in the two categorical setting. Yeah.
So is the monoidal structure on cat direct product, or somehow would it be?
The monoidal, yeah. Yeah.
So these functors, these composition functors should be monoidal or something. I don't.
No,
Some
because
fashion, or maybe I'm confused. Yeah.
No, I mean, this is now just a category, right?
Okay, sure.
And so then you just have a functor to another category.
By enrich over, do you mean Cij is
It's a small category. Yes.
monoidal category?
Yeah. No. So it's so Cij enriched over small categories means precisely that Cij is a small category. Yeah.
But oh, okay, yeah.
So this is so somehow the saying it's enriched over cat
Yeah.
is the slick way of saying it, and I could have stopped there.
That's monoidal category.
Yes,
but
yes.
not in the elements.
Yeah, exactly. So So I don't know, when I first saw the definition of a two category as a category enriched over small categories, I had no idea what that meant. And so this is why I always say it has objects, one morphisms, two morphisms, and this is what it looks like. Okay, so that's a two category. And the two category that everybody really knows is cat, the two category of small categories. So objects are small categories, one morphisms are functors, two morphisms are natural transformations. So anybody who's ever seen any category theory knows a two category. Yeah. Okay. So let's give a more complicated example. And the reason why I'm giving it is because earlier I said an algebra is a representation of an algebra is a functor from my one object category to vect. And then I say, well, we want to upgrade that. We want to look at some two representations. And then it'll have to be a two functor to something. And the question was the something. And the answer is always the something should be the thing that you're enriching over. Yeah, remember, I asked for an algebra, I asked my category to be linear, which means it's enriched over vector spaces, over the category of vector spaces. So morphisms are vector spaces, which means I then want to take my functor of the representation to the morphism, to the vector spaces. So this is going to be the thing where we're representing, and also the thing that will be enriched over in the case, in the cases that I'm interested in. So the objects are small categories, which are additive. So they have a direct sum. They are k-linear. So morphisms form vector spaces. And they have finitely many indecomposable objects. So an object is indecomposable if it can't be written as a direct sum of other objects. And they only have finitely many of those up to isomorphism. And the vector spaces that I get as my morphism spaces have to be finite dimensional. Okay. So if you're familiar with representation theory, so if you take a finite dimensional K algebra and look at the projective modules over this, or so earlier today we had a talk which had some projections. Yeah, so I would call these things idempotents. So if E in an algebra is a projection, then AE is a projective module. Yeah, just by multiplying on the left with A. And so if you look at all of these kinds of things and look at the category of those, then that's precisely such a category, and all categories of this form arise in this way. Yeah, you might just have to find the algebra A, but it's possible. Okay, so these are the categories that will be our CIJs, and this is also where we're going to be acting via our representation. And then, well, I have k-linear additive categories, so my one morphisms, they need to be functors, but they better be compatible with that structure. So I ask for k-linear additive functors. And the two morphisms are just any natural transformations of such functors. Yeah, so two morphisms have no restrictions whatsoever. Just any old natural transformation will do.
CIJ has to be, what does it have to be, CIJ?
So no, what I'm saying is in the examples that motivated us, the CIJ that we had on the previous slide, yeah, these morphism categories in our two categories, they happen to be in here. They happen to be such categories. Yeah, so this is why I introduced these categories, because these are the categories that we will, our particular two categories. I mean, in principle, a two category can be enriched over any small categories. Yeah, so whereas we want specific ones that match what comes from the examples in representation theory.
Why do you ask for finite dimensional morphism spaces?
Well, so this I should say something about this. So there are some so we don't necessarily need finite dimensional morphism spaces for things to make sense. But when we first started developing this, and maybe actually let me come back to that on the next slide. Yeah, because then I can say this a bit better. Okay. So one thing that I wanted to point out is these categories in here, these categories of finitely generated projective modules, they are hardly ever abelian. So they're abelian only if my algebra is semi-simple, and the vast majority of my algebras are not semi-simple. Okay. So and not being abelian is where things really differ from the EGNO approach of tensor categories, which are always assumed to be abelian. Yeah.
Is the one morphisms are the same as bimodules, which are projective on one side or something? Eilenberg laws. Like, can you think of every functor as tensoring with a bimodule?
You can, yes, you can think of that as tensoring with bimodules, but they don't necessarily at this point they don't have to be projective on any side. Oh no, on the left. Yeah, sorry. Yeah, sure. They have to be projective on the left, but then that's exactly, you can think of bimodules. Yeah. Okay, so I just wanted to stress that point because I think lots of people here are sort of familiar with tensor categories, fusion categories, and fusion categories obviously are semi-simple, but even tensor categories are, in the EGNO sense, are assumed to be abelian, and here things are not abelian.
What does abelian mean in this context?
Oh, an abelian category is a category where you essentially have kernels to every morphism, and you have co-kernels, and then there are things like every monomorphism every monomorphism is the kernel of its co-kernel, and every epimorphism is the co-kernel of its kernel, or something. So there are lots of axioms, but essentially, if you took all A modules, so morally speaking, abelian categories are categories of A modules where you take all A modules, whereas here you only take the projective ones. Yeah. So there is a way of passing from this to abelian categories, but the problem that we then encounter is, again, let me come back to that on the next slide. Okay, because when we then started trying to develop some general two representation theory, we thought, well, okay, if you do a first course in representation theory of algebras, you might want to think about finite dimensional algebras, or at the very least Artinian algebras or something. You might not want some crazy non-Noetherian whatever things. Yeah. So we thought, okay, what are some safety assumptions we can put on to make things controllable and to sort of stay in some vaguely finite dimensional world. So we said C is finitary if, so two categories called finitary if it has finitely many objects, and that's pretty superfluous. Yeah. So since then, a PhD student of mine has certainly countably many objects works fine. We didn't really look at, I don't know, large cardinality is always sort of when you need set theory, when you get into the cardinals and ordinals, and that makes me very uncomfortable. So I didn't really go there, but yeah.
It's up to isomorphism.
Hmm?
Up to isomorphism.
No.
Straight.
The objects are just objects. Yeah. So we don't have, so you can, because you have between the objects, you have morphism categories. So you can ask whether two objects are somehow equivalent if you have, but I mean, here we just really take the objects on their own. Yeah. But certainly, I mean, if you blow up the equivalence classes, it won't matter. Yeah. Okay. And now we are asking every morphism category to be one of these nice projective modules of a finite dimensional algebra type categories. Yeah. And this is so we don't really need so the reason why we're asking for finite dimensional morphism spaces is because we wanted categories of the form A-proj, and we're very comfortable with that for finite dimensional algebras, and then we have finite dimensional morphism spaces between two finite, so yeah, this sort of comes for free. If you look at, and some of our results will actually be using methods from finite dimensional algebras. So if we go to infinite dimensional ones, things will have to be done differently. And this is something we're working on, but it's sort of work in progress. Yeah.
Just a very
So is algebra part of the structure? So is it you choose an algebra, or there exists an algebra such that Cij is isomorphic to the category of projective?
Well, it depends on what you want. So what this says is there exists an algebra such that Cij is equivalent to A-proj.
It's not isomorphic.
Yeah, equivalent. So I mean, these are categories, right? So asking for two categories to be isomorphic is just way too strong. Yeah. In particular, since I was lying, because I don't think the category A-proj itself is small, and I certainly want small categories. Yeah. But so what you could say is they have isomorphic skeletal categories. Yeah.
Describing the type of algebraic thing, like the two categories, you will want to do the representation theory for.
Yeah, this is the type of two category that we want to do representation theory for. Exactly. Okay, so of course then, given that I'm asking for k-linear categories as my morphism spaces, k-linear additive categories, I want composition to be bi-additive and k-linear. That's sort of fairly natural. And then we threw in an assumption that the identity one morphisms are indecomposable objects so the identity on I has to be an indecomposable object in CII. And this is again absolutely not necessary. You can easily pass back and forth between these not being indecomposable, and then you can so it's just sort of, I don't know whether this means anything to you, but if you have an algebra, you can look for a complete set of idempotents and split it up, and that just often makes it easier to handle. But it's not anything that you need to have to consider the algebra. Yeah. So this is again, this is completely unnecessary. It just you can, but also you don't lose generality when you assume it. Okay. Okay. So. And the moral of this is that you should think of these finitary two categories as the two analogs of finite dimensional algebras. And now you might complain and say, well, yes, but you told us what's being categorified is Kac-Moody algebras, which are vastly infinite dimensional in general. And yeah. And of course, the answer to this is we can retreat to the finitary case in some cases. In finite type, we can take certain quotients. And then if we want to treat non-finite type for the Kac-Moody algebras, then we have to expand methods a bit, and that's something that PhD students can do. Yeah, did you want to ask something? No, okay. Okay, so these are finitary categories. So here's an example. Suppose B is just any old finite dimensional algebra. Pick your favorite. Now I define a two category, which just has one object. So you can also think of it as a monoidal category. And my one morphisms are sums of direct summands. So I certainly need B as a bimodule. Yeah, because that's the idea. So I'm going to take some BB bimodules, and my horizontal composition is just going to be tensoring over B. So since I need an identity, I should certainly be taking this bimodule, the regular bimodule. And the other bimodules that I take will be direct summands and direct sums of those direct summands of B tensor over K with B. So this is a projective bimodule. And I allow all projective bimodules. Yeah, so I take the identity and all projective bimodules. And this is a nice two category. And then two morphisms are just all natural transformations of these, which is the same as saying it's all bimodule morphisms. Yeah. So two morphisms are just all bimodule morphisms. But now, in Lie theory, things and most of the objects that have been categorified have some vaguely Lie theoretic flavor. And I use Lie theory very, very broadly. I count Hecke algebras as a Lie theoretic thing because they show up in finite groups of Lie type. Or yeah. So anything that, so for me, a Lie theoretic object is anything that is vaguely related to Dynkin diagrams, more or less. And these usually have some kind of involution. or something. Yeah, so if you have a Lie algebra, if SL2 has generators E, F, and H, and you can swap F and E, yeah, and you can do that more generally if you have with your Chevalier generators for a Lie algebra. The Hecker algebra has an involution, a fairly canonical one, and so in the categorification that will show up as adjunctions. So we say a 2 category is fiat or quasi-fiat if it's finitary in the first place, yeah, and moreover we have some adjunctions. So okay, so this is a bit imprecise. So it's fiat if you have if F double star is isomorphic to F, and it's quasi-fiat if you don't ask for that. Yeah, it's just sort of so this is what's often called rigid in the EGNO literature. And so in the example that we had earlier, so this is quasi-fiat if B is a Frobenius algebra, because then the adjoint of B tensor B, if I view it as an endo functor of B modules by just tensoring with this bimodule, then this is B star tensor with B. And of course, if I have a Frobenius algebra, this is an injective B module. And if my algebra is Frobenius, that means it's again projective. And so then I'm happy. Yeah. And if I want it to be fiat, then I need B to be quasi-symmetric. So Frobenius means every projective module is also injective. So projectives and injectives coincide. And quasi-symmetric means that if I look at the top of my indecomposable projective and the socle, so the unique simple submodule and the unique simple quotient, those are isomorphic. And if I have that, then my CB will be fiat. But again, remember, these Frobenius algebras are very, very far from being semi-simple. So they're not necessarily any kind of matrix algebras or anything like that. Okay. So, but in particular, that means that these categories are typically not abelian, because my algebras, so they're only abelian if my algebra is semi-simple, and I'm so in the interesting cases for us, the algebras are not semi-simple. And now I can say so I was saying earlier that, well, pretty much every abelian category is of the form A mod for some algebra A, and I'm only looking at A proj, but obviously you can go back and forth, right? You can say, well, if I have A mod, I can just restrict to A proj. On the other hand, if you look at finitely generated modules, you can certainly write them give a projective presentation for them. So you can recreate all modules from your projective ones. So we have the option of going to some abelianization and work with abelian categories, but the problem is that we're on the level of A proj, we have these adjunctions if we're fiat. And if we pass to A mod to the abelianization, then we lose the adjunctions. Then we typically won't have any. Yeah, so if you take a non-semi-simple Frobenius algebra and you look at the category of projective injective modules, then you have adjoints because you could dualize, because the dual of a projective will be an injective, morally, that's the idea, and you stay in the same category. But I can't. So it all comes down to the fact that the adjoint of a bimodule M would be hom M blank. Yeah, the adjoint of tensoring with M is hom M blank, and usually that can't be expressed as a tensor functor for arbitrary modules of arbitrary algebras. So in some sense, what's very different to the EGNO setup in our setup is that we always have to make a choice. Do we want to have something abelian or do we want to have adjunctions? But we can't have them both. And we somehow, so a lot of what we do is playing those two sides against each other. Yeah. Okay, so now let's talk about Zagel bimodules, because essentially what I want to do today is I want to show you a theorem about circle bimodules that sort of gives a flavor of the kind of things that we've been doing. Okay, so let's say we have a Coxeter group. So what this means is that it has some generators. And so S is some set. And the generator squared to the identity. And the only other relations I have is that for every pair Si and Sj, I give some multiplicity, some multiplicity, some order to the product of Si with Sj. Yeah, this is the most general definition of a Coxeter group. Okay, and then you can define something that's called a reflection representations, where these Si act as reflections. And then you can define the co-invariant algebra, where you look at the algebra. So you can view this, so this is called the symmetric algebra on the vector space, but what it really is you pick a basis of your vector space, and you look at polynomials in those basis elements, just formally, okay? And then of course, because your Coxeter group acts on V, you can look at what it does to the basis elements and say you've chosen a nice basis where it just permutes them and so on. You can look at the polynomials that are invariant under the action of this group, okay? And then you want to kill those. But of course, you can't just kill them all because the identity polynomial is certainly invariant. So you better take the invariance of positive degree and the ideal generated by those, and then you mod out by that, okay? So this is the co-invariant algebra, and this construction with the reflection representation and so on, let's from now on assume that we take a finite Coxeter group, okay? Because in principle, I didn't have any restrictions on S, but I don't only want finitely many generators. I want to choose my Mij such that the whole group W is finite for the rest of this talk. So a lot of this will work for infinite, but a lot of what I'm going to say about the true representation theory of the thing that I'm going to construct won't work
Will it
yet.
work for complex reflection groups?
Not so far.
Okay.
I mean, I'm fairly sure that something is possible to do, but this is really just for Coxeter groups. Okay, so now we have our co-invariant algebra. This is then, if W is finite, this is a finite dimensional algebra, but it's not semi-simple. Yeah, it's not semi-simple ever unless you have the trivial group. But what I can do is, so I've killed the things that are invariant under the whole group, but I might still have some things that are invariant under just certain reflections, but not the others. Okay. So I can take the subalgebras that are invariant just under one reflection, one of my generating reflections, and then I can take my co-invariant algebra, tensor it with itself over this subalgebra, okay? Now notice that that is a CC bimodule, because I can multiply on the left by C and on the right by C. So that's something we can do. And now the category of circle bimodules, or you could also call it the Hecker-2 category, because it categorifies the Hecker algebra associated to this Coxeter group, has just one object. And the one morphisms, well, let's just say they are direct sums of finite tensor products over the co-invariant algebra itself, yeah, of these generators Ci that I defined up there. So I just take bimodules of this form and I tensor them up over C. They're CC bimodules, I can tensor them. And I see and then I decompose them. They might not be indecomposable anymore, but I could just look at what are the direct summands, and I take everything I can generate in this way. Okay. That's the category of circle bimodules.
Sorry, did you say are the CIs themselves undecomposable?
The Ci themselves are indecomposable, yes. But once I start tensoring up they might do whatever. Okay. And then two morphisms are just all bimodule morphisms. So I've said I identify this with CProj, and then I can take endo functors, and then I take all natural transformations. That's just if I'm desperate to be in the strict setup, because you can argue that if I just look at bimodules, I have a bicategory. Because technically speaking, not even composition, not even tensor product is strictly associative. Yeah. Sort of almost strictly associative, but yeah. Okay, but that's just sort of technical nonsense. But in principle, you just take these bimodules, you tensor them up, you look at what you get, and you allow all bimodule morphisms between them. That's the two category of circle bimodules. And so if my Coxeter group is finite, which from now on I'm always going to assume, this S is fiat. So it has all these nice properties. The morphism categories are of the form A proj for some algebra A. And it has adjunctions. So in particular, the adjoint of this is itself. And it categorifies the Hecke algebra in the sense that if I take the Grothendieck ring of it, and well, I mean, if I want an algebra, I need to tensor that with some field or something, then I really get the Hecke algebra back, the Hecke algebra associated to that Coxeter group. Okay, so this is 1-2 category that you might want to study. And of course, what's the first thing that if you look at classical representation theory, what's the first thing that you might want to study? You might want to find simple modules for an algebra. And so, of course, this is also the first thing that we are trying to do, and this is going to be what I'm going to be talking about for the rest of the talk. So when did I start? Sorry, I forgot. I go until 4:30, right?
Yes.
Yes. Okay. Okay, good. 40?
Sorry, not 40.
20, 22,
25 minutes.
Yeah, okay. Okay.
Categorifies the Hecke algebra of W, S. So it categorizes the Hecke algebra.
Of W. Yeah, of that Coxeter group. Yes, I didn't write it, but I
And the
said.
choice of S somehow.
Yeah, but it's well, it's somehow independent of the choice of S, but
Okay.
but up to isomorphism. Yeah. Okay, so let's do the baby case example. Let's take the smallest non-trivial Coxeter group. It's just a symmetric group on 2 elements. So it was 1 generator, and that squares to 1. Then my co-invariant algebra is just dual numbers. So this is a very, very nice controllable 2-dimensional algebra that I feel like I understand really, really, really well. And then what is then of course I only have 1 generator. And what's that? Well, I just take this and tensor it over my ground field, which is complex numbers, with itself. Okay. So that's a bimodule. And then I can look at what that generates, and what you'll find is that when you tensor that with itself, you just get twice itself. So you're not actually really generating anything new. So those are also the only indecomposable things. But what I want to talk about here is how you can actually get some knot homology or link homology out of this, because that's somehow related to the conference. And I am not a knot homology, link homology person. Yeah. But this I understand. So if I take some kind of braid diagram and close it up to get the associated knot or link diagram, then I can associate a complex of bimodules, of CC bimodules, where I orient it, I walk along, I have overcrossings and undercrossings. I never know which one is which, but it doesn't matter. There are 2 of them, two kinds. To one of them, I associate this complex. So what's that? CS is the tensor product of C with itself over my ground field. So I have a very natural map that just multiplies things together. And then this is kind of going in the opposite direction. This is in some sense, so this is a Frobenius algebra. The dual basis of 1 and x is, well, I mean, 1 is dual to x and x is dual to 1. And so I take somehow everything tensor its dual, which is then gives me x tensor 1 plus 1 tensor x, and I have to scale by 2 in order to, because it's 2-dimensional. Okay, so and these are now complexes of CC bimodules. And now I can just walk along my knot diagram and tensor them up whenever I come across a crossing. And that gives me some bimodule, some complex of bimodules, possibly very big. But now I can compute Hochschild homology of this, and this is the Humflee homology of this knot. Yeah, so this really comes, so for people who might have heard the word Humflee polynomial, that was categorified to Humflee homology, and this is really what it is. And I've just given L plus and L minus. I somehow I'm not very good with BEMA, and so I kind of would have liked this to appear when I showed this, but I didn't want to show this bit yet, and I didn't know how to make that
So
work.
it's triply graded.
Yeah.
So
No.
the 3
wait.
grade? If it's
Well, so
Humflee
I mean,
homology-
I've been sweeping a lot of things under the rug because Zergel bimodules themselves come with a grading. Yeah, so because you would grade your coinvariant algebra by putting x into degree 2.
Okay.
And then of course you get a grading from the bimodule. Yeah. And then from
homological grading.
yeah. Okay. So but now we want to do some representation. Yeah, sorry.
Was there on the previous slide you choose C as the polynomial ring modulo x squared?
I don't choose it.
It has to be.
This is the coinvariant algebra associated to this Coxeter group. Yeah. Okay, so now we want to study two representations. So what is a two representation? And I've already said it, yeah, because a representation of an algebra is a k-linear functor from my category that I view as my algebra to vector spaces. And I said the reason why we choose vector spaces is because that's what we're enriched over. So here we need to take a k-linear 2 functor from our 2 category that we want to represent to the thing that we are enriching over, which are these categories that are equivalent to finitely generated projectives over a finite dimensional algebra. Okay. So what this means, if I spell it out, is that to every object, I associate the category of finitely generated projective modules over some algebra. To every one morphism, I associate some functor, some additive functor between them, k-linear additive. Yeah. And to every 2 morphism, I then associate a natural transformation of functors. Okay. So that's a 2 representation. And so the example is that we always have the Yoneda embedding. You know, we can just take the 2 functor Ci blank. And if I plug in my object J, then by definition, I land in here because that's what my Cij has to be. And this is sort of, if this thing isn't a representation, then you're taking representations in the wrong thing. Yeah. This is why you want to take representations in the thing that you're enriched over. And I kind of defined Zergel bimodules via a defining 2 representation because I said we identify our one object with projective modules over the coinvariant algebra, and then we have these bimodules which we can also view as endofunctors of that. Yeah. PI, so we call this the principal 2 representation. We can't call it projective even though it is, but there are others. But so this is a 2 functor, yeah, because if I plug in my object I, my object J, then I get Cij, which is one of these categories in here. So I take something in here and I spit out something here.
It's like a regular representation.
Yeah. Well, it's in some sense a direct summand of the regular representation or something. Yeah. Because we fixed I, so we won't get everything. Yeah, we will never see any Ckj. Okay. Okay, and now we want to look at simples. And a 2 representation is simple if And this is a bit technical. So if I look at all the categories that I spit out when I apply my two-functor, then I can look at the action of that. And I want no ideals in these categories. So an ideal in a category is a bunch of morphisms which is closed. So a set of morphisms that's closed under pre and post composition. Yeah, like an ideal in a ring. And I don't want any such ideals that are stable under my action by my two category. Yeah. So that's because if I have a C stable ideal, I could take a quotient by it, and then I wasn't simple. So finding this definition wasn't totally trivial, because it turns out, so if you think about simple modules in classical representation theory, there are lots of equivalent definitions. It doesn't have any non-trivial submodules. It doesn't have any non-trivial quotients. It's generated by every element. And somehow it turns out that all these notions categorify to different notions. And the reason why this is the right one is because this is the one with which we can get some meaningful Jordan-Herder theory. And so we can look at filtrations and so on and so forth. Anyway, so that's a definition of simple. Don't worry about it too much. It's just, I'm telling you, there is a correct definition of what it should mean for a two representation to be simple, and we want to understand simples. So how could we go about that?
Does Kapranov-Voevodsky 2-vec sit over your target in a nice way?
So as far as I understand their 2-vect, this should be essentially the sub-2 category of AKF, which consists of the ones where the algebras are semi-simple. That's my understanding. But I find it very difficult. But I think that's what it is. Okay. So now we want to classify simple two representations for interesting two categories, and the interesting two category that I'm claiming we should talk about is Zagreb modules. So
Do you have a question? Do you have a definition of decomposable representation?
Well, you can, in some sense you can just say if it's not the, yeah, I mean you can define it.
It will simple imply that?
Simple will imply indecomposable. Yes. Okay. So now let's take a Phi 2 category, and one thing that's quite crucial for us. So if you look at the fusion category, this will all become completely trivial, but in our case, this gives a very, very rich structure, what I'm going to talk about now. So we can look at the isomorphism classes of indecomposable one morphisms, and we can define an order or a pre-order, partial pre-order technically, where we say one morphism is smaller than the other. So my one morphism is smaller than another if I can get the bigger one, the wannabe bigger one, as a direct command of taking the smaller one and multiplying by something on the left. Yeah? So you can think of somehow of this, if you just think of rings or something, as the bigger one is in the ideal generated by the smaller one. Except here we have to be able to decompose things into direct commands and so on and so forth. And then, of course, we can look at equivalence classes with respect to this partial pre-order. And those are called left cells. And then we can do the same thing on the right. We get right cells. Or we could allow ourselves to multiply on both sides at the same time. And then we get two-sided cells. And so you can easily see that, so in our definition, one is obviously always in the smallest cell, because from one I can go everywhere without even taking direct amounts by just multiplying by the thing that I want to go to, right? On the other hand, you can also see that in a fusion category where everything is semi-simple and has an adjoint, from everything you can get back to the identity, because you will necessarily have the identity as a direct command of a theta times its adjoint. Yeah, so for fusion categories, this becomes completely trivial. But if you don't have that, then this becomes a very rich structure that's really helpful. Yeah.
So, you have adjoints, that just doesn't imply the identity to summit. You just co-evaluation doesn't.
So it just implies that I have from FF star, I have a morphism to the identity, but that doesn't have to split. It doesn't have to be a direct command. Okay. Okay. And then we also need H cells, which are intersections of left and right cells. Okay, so that's just how H cells are defined. So let's look at an example. So in Zergel bimodules, the one morphisms are precisely labeled by elements in my Coxeter group. And in particular, the one morphisms descend to something called a cellular basis, which is the Kastanlustig basis. Yeah. So that's just a fact. And but it implies that the cell structure is really there are also things called Kastanlustig cells, and we really get those back. So let's look at this in a slightly bigger example than we had earlier. So if we look at the Coxeter group of type B2, which is the same as C2, this is just the dihedral group with 8 elements. And this is what the cells look like. So I have the identity in its own left, right, two-sided cell and H cell. I have the longest element in its own left, right, two-sided cell and H cell. And then in the middle, I have a big two-sided cell, that's this block. And the way to read this is that the left cells are the columns and the right cells are the rows and the H cells are the little squares. Yeah. So this is how to read this sort of diagram. Okay. So now we can, a very, very powerful tool that comes from the cell structure is that if we now take some H cell, that if I draw this diagram is on the diagonal, yeah, then I can construct some smaller two category, and don't worry about the steps. But essentially what we do is we kill everything that comes from bigger two-sided cells. We just quotient out by that. And then we look at just those one morphisms given by the identity. So every H cell will have a unique identity attached to it, even if I have lots of objects, but it will start and end at the same object, and then I have a unique identity. And the things in this H cell. And then I get a much smaller two category, which now has fewer one morphisms. And then I still want to kill some ideal that is just superfluous for us. Yeah, but don't worry about the precise definition. Okay, so if we go back to the example and we take so let's just go all the way back. So I want to take my H cell to be this one. Yeah, that consists of S and STS. And now my construction. So this thing has 8 indecomposable one morphisms, which is already quite a lot. I mean, okay, maybe not so much, but if I now, oops, that was too far. If I now look at my S sub H, so here the two category was S, so my H becomes the index there. Then I suddenly just have my identity and I have my indecomposable one morphisms associated to these. So now I'm down to 3 indecomposable one morphisms. And the theorem that really makes things tractable is that if I want to know all non-trivial simple 2 representations of my 2 category, then I can look at all, then I can pick one H cell in every 2-sided cell, construct the CH, look at the non-trivial 2 representations for those, and take all of those. Yeah, so I look at a number of small 2 categories rather than one giant one, and I get a bijection. And this is actually more than a bijection. It's somehow an equivalence of 2 categories of simple 2 representations. But let's just stick with the bijection for now. And so the upshot is that we can concentrate on these CHs, which are much, much smaller. And this is called H cell reduction. Okay, so now Lustig did something on the decategorified level, did something very similar. He showed that he can associate to every H cell of his Kastanlustig cells on the Hecke algebra level, a so-called asymptotic algebra. And then he gets the same sort of bijection, yeah, between simple representations for the Hecke algebras and simple representations for all these asymptotic algebras where he picks one H cell in every two-sided cell. So now the question is, well, can this somehow be lifted? Yeah, can this be categorified? And so the idea behind this is, again, that asymptotic algebras are easier to understand. So yes, so this has been categorified in some sense, because Lustig, again, for circle bimodules, to every H cell associates some kind of asymptotic bicategory, which is called A sub H. And so it categorifies the asymptotic algebra that he associated on the decategorified level. And this is now a fusion category. Yeah, so this can be studied using Egnor methods. And in particular, for any finite Weil group, this is very, very well understood. And the simple two representations for that have been classified by people like Ettinghoff, Ostrich, and lots of others. Yeah.
What fusion category is it?
Oh, I mean, it depends on your A and H. Sometimes you get rep G, sometimes you get vec G for something, or I think SO N shows up in some. So it really depends on what your W is, which diagonal H cell you've chosen, and so on. But if W is a finite Weil group, then you can choose enough H cells so that these are precisely understood. Okay. So what we would like to do is we would like to relate the two representations of the S sub H's, which are our quotients, which are still very far from semi-simple, but they're much smaller than the whole category of circle bimodules, but they're still complicated. They're still not semi-simple. And we want to relate them to those of the A sub H's, okay, which are understood. And so, okay, now at the latest, I want to assume finite Coxeter group, but I already assumed it earlier to make some things nicer, to not have to say too much in detail. So then there is something called a cell two representation, which I don't want to define, but we can associate that to every left cell. And in particular, in my CH, I now only have two cells. I have the identity cell and I have my H. So the H is in particular a left cell. Yeah, because the left cell, right cell, a two-sided cell, it's everything. And this is so I'm not telling you how to construct this, but it can be constructed, and it is simple by construction. And so for this, we can define, we can prove a double centralizer theorem. Yeah, so this first statement here is completely trivial. It just says that everything, so that the action of these circle bimodules commutes with everything that commutes with them. Yeah, I mean, that's sort of a tautology. But then you can use this to get some equivalence between certain types of these endomorphisms that commute with them and the things in H. Okay, so I mean, this is incredibly technical. I don't want to go into details because I only have 2 minutes anyway. But there is some, you might have seen a double centralizer theorem, say Schur-Weil duality, and so this is somehow a two-categorical lift of that. And I'm stating it here for circle bimodules, but this works for any Fiat two category and any simple two representation. So I don't need it to be a cell two representation, and I don't need it to be circle bimodules. Okay. And then the miracle somehow is that this thing here is, so the thing on the other side of Schur-Weil duality, if you want, yeah, of your double centralizer theorem for your S sub H, is actually the A sub H. Okay. And so the whole point of double centralizer theorems in classical representation theory is that it gives you control over how the simple modules correspond. Yeah, and so this is precisely what we get from there. So putting those together, we now get the bijection between simple representations of A sub H and non-trivial simple representations of S sub H. And of course, now, because we already know that if we run over all the S sub H for a choice of H cell in every two-sided cell, we can put that together. And again, I mean, this is stronger than what I'm stating. This is a bioequivalence of two categories of simple two representations, but never mind. And we can put that together with theorem one, with the other theorem, where we said that if we run over all of those, we get all. Oh, this was supposed to be. This was supposed to be an. Oh, now I'm confused. So I mean, this is just our H cell reduction, what I've written here. Yeah, this is just recalling the H cell reduction. But now, of course, given that those are the same as those, we can put this together to get a classification of simple two representations of circuit bimodules. And this is the sort of thing that we've been doing. And I wanted to make two remarks. So I said if W is a finite Weil group, then these asymptotic bicategories, these fusion categories are well understood. So there are some cases, Coxeter type H3 and H4. I don't even know what these groups look like, but there are in H3, I think there's one two-sided cell where for no H cell is the asymptotic bicategory understood, and in H3 there's also a handful of. Yeah, so in those cases, there are some problems where the asymptotic algebra is not understood. The reduction theorem still holds, but yeah.
So I'm a little confused. Are these AHs, are you saying they're fusion categories?
Yes, the AHs are fusion categories,
Okay.
and in all Coxeter types, apart from H3 and H4, they're understood and their simples have been classified.
Okay, and maybe just to ask another, maybe a simpler question. So what is a two representation of the fusion category? It's a
It's what so yeah, so this is what EGNO call a module category.
Okay.
Yeah, I should have said that. Yeah.
But is a simple module category or a simple two representation imply the category semi-simple if it's a fusion category?
Yes.
Okay.
Yes.